Alright, so we're going to be going over a review of derivatives and rate of change. So finding the rate of change at a point is the same as finding the slope of the tangent line at that point. So let's say that we have curve C, which has the equation y equals f of x. To find the tangent line to C at point P, which is going to be a, f of a, we first learned how to find this slope using a second point, which we say is q, x, f of x, and we use the slope formula that we knew before. So as we find the average rate of change, we do the displacement over time, so we would get this equation. But as we want to find the instant rate of change at this point P, we make this displacement smaller and smaller and smaller. So as this distance between these 2 points is getting closer to 0, we're now finding the limit as x approaches 0 of this equation. So this was then how we found velocity at a certain point. Okay, so now we're going to be looking at a different kind of problem where we're given a table with years and numbers of some kind of data. So we're going to be looking at the rate of change of this data over a set period of time. So part A is asking us to find the average rate of change during these 3 different times. We're going to use this rate of change formula. So 2005 to 2007, we're looking at 67 minus 38, and then there's just 2 years in between those times. 2005 to 2006, 54 minus 38 over 2. And 2004 2005 would be this is just 1 year, and this is just 1 year. Alright, so for part B, it's asking us to use the information we previously solved for in order to try to find the instantaneous rate of growth at 2005. So we solved for the year after 2005, being 16, and the year before 2005 as being 9. So when we add those two and divide by 2, we get 25 over 2 p per year in 2005. So this is the estimate that we're able to get using this average rate of change formula. Alright, so part C is asking us to find the instantaneous rate of growth at the same place, 2005, using the slope of the tangent line. So all we're given is this table of data, so we're not able to use the derivatives. Instead, we're going to, here's the curve, 2005, we're going to just have to estimate using the points that were given at 2004 and 2006. So we're going to do the y at 2006 and the y at 2004, 54 minus 29 over 2006 minus 2004. So what we get is 25 over 2 p per year in 2005. So this is the same number that we got here using a different evaluation. So it's not, you won't always get the same time, but this problem is just illustrating 2 different ways that you can solve for rate of change without using derivatives. So continuing to talk about the instant rate of change, which we know is the limit of change of x approaching 0 of change of y over change of x, which is back to this original formula, which is also equal to this. This limit is accepted as being equal to f prime, the derivative of x1. So this confirms the derivative f prime of a is the instantaneous rate of change of y equals fx with respect to x. So when these are equal, y equals fx, the derivative is equal to the instantaneous rate of change. So now we're going to take a look at this word problem using the equation we just went over, right here. So a ball drops 450 meters from the top of a building and we're looking to find the speed of the ball when it reaches the ground. And it gives us this function for time and distance. So this would be the distance traveled, and this would be the time. So as we plug in, and we find the limit as x approaches 0 of this equation, we solve and get 9.8 equals a. So this is where we bring in our other knowledge of derivatives. We were given that f of t is equal to 4.9 times time squared. So using the power rule, we bring down the 2, and then we subtract 1, and we get the same thing as we did from the other formula, 9.8 times t, or a. So now we're going to solve what it says to do in the original equation. We're going to find the speed after it's traveled 450 meters. So for the original function, we're going to solve for what the time is when it reaches the bottom. It's going to travel 450 meters in this time. So then we find that time is equal to 450 meters divided by 4.9 and take the square root of it. So we're trying to find the velocity at that time, which we solve for right here is 9.8. So the derivative of the original function, the derivative of the position function, is equal to the velocity. So then we plug the time in here, and we get that the velocity at 450 meters is this, which is approximately 94 meters per second.